All right, so let's do a quick problem involving a little bit of graphing that would be appropriate to this unit. So the problem looks like this. I really should have had it crafted a little bit more than when I started. Um, so we have a graph that looks something like like that. And what I want to know is I want to, at every 2-second interval, at every 2-second interval, we'll call this one the 0 to 2 is A, B, C, D, and E. So every 2-second interval, I want to rank the change in momentum. So we're going to rank, our change in momentum. So going through here, the first task that we would have is to make the connection between change in momentum and impulse, which is what this graph is giving us. This is an F and delta t graph, or F versus delta t, which means F times delta t, the area, would be the impulse. And so we can use the area to figure out what the change in momentum is. So this area right here is a base of 2 and a height of 3. So that's 1/2 base times height for a total of 3. So that's our change in momentum is 3 Newton seconds. In the next region, it would be base of 2, height of 3. It's not a triangle, so it just works out to be 6 Newton seconds. That seems like it's the winner. For this one here, we kind of have to chop it up a little bit, most likely. Well, I'm actually going to do this a fancy way and say, see this triangle right here? This is a triangle that is 1/2. This would normally be 6, but I'm missing a half, so this must be 5.5. That's a good way to go about that. My next one here, this has an area of 2, and this one here has an area of -2. If I was going through ranking these, probably I should have been more specific and been like the magnitude of the change in momentum or something like that. But I would loosely say that the change in momentum, the ranking here should be something like B is the greatest change in momentum. And then we have C, which comes after that, then A that comes after that. And then depending on whether we're looking at the negative sign or if we're looking at just the magnitudes, we would either say D equals E or D is greater than E if we want to keep the negative in mind. That would be one kind of problem that you might see with these. And this force versus time graph is a really common one on AP exam. Another thing that we might be asked to do is we might be asked to look at, to turn one of these graphs into a momentum versus time graph. So to do that, I can actually graph it by hand because the area under this curve represents the change in momentum. So if I started from 0, then my next point, 2 seconds later, my momentum has changed by 3. So I would be there. My next point at 4 seconds would be 6 further up, which is here. My next moment would be 5.5 further up, which would be all the way up here. Let's see, that's 5.5, puts me just right there. Then I go up 2 more, and then I actually come back down 2. I can kind of draw this in. It looks like it's going to be a graph that looks something like that for my momentum versus time graph. An important thing to keep in mind is a relationship that exists here. We already know that if we have an acceleration versus time graph and a velocity versus time graph, the area under the curve of this graph will be the slope of that graph. The same relationship exists between force and momentum. The area under the curve of a force versus time graph is the momentum, and actually the slope here is actually the force. So the slope there is the force, the area under here is the change in momentum. So there's a relationship that exists there that you may be tested on. That pretty much hits everything that I wanted to do with this. Just talking about that area and slope relationship and kind of doing it as a practice problem. So thank you for watching. I hope this helped.